Microplastics, that's what we're all here for, has become quite the buzzword in the recent decades with much ado about it in the media. And it's probably justified, seeing as the ubiquity of microplastics in the news only complement its ubiquity in where they're showing up in everything in our lives, from our water, our soil, marine animals, to now human placenta. But it benefits us to understand microplastics through the lens of macroplastics and global plastic production, which has now exceeded 8 billion tons since mainstream production began in the late 1900s, with 56% of all that plastic coming from the new millennium. What's sad is that only a small percentage of the plastic is actually in use. 40% of all plastic products go to waste. That calculates out to about 300 million tons of plastic waste a year. And it's long been thought that a lot of this plastic that we produce, or the plastic waste that we produce, ends up here in marine gyres across the Earth's oceans. These gyres house a lot of garbage which were sailed over from global coastlines. We've all seen horror pictures of giant piles of trash on various coastlines. And this has to do with how ocean currents flow. And you'd think that the millions and tons of plastic that we produce are living here in these gyres. But when ocean cleanup researchers crunched the numbers, they found that only 1% of what million tons of plastic we produce or we throw away into the ocean are actually living here in the gyres. That's 99% of plastic that's completely unaccounted for, possibly already on its way to microplastics, or sunk deep in the ocean floor, or just living in the ocean as plastic fragments. The same researchers also surveyed macroplastics found in one particular garbage patch in their well-known cleanup of the North Pacific garbage patch. They found that the plastic found in these gyres were from the 1990s or earlier, and they did this by looking at macroplastics that had production dates on it. This is interesting because we saw from plastic production charts that the world plastic is overwhelmingly millennial. In the same report, ocean cleanup researchers posit that the newer plastics are constantly circulating on and offshore, seeing repeated cycles of beaching, fouling, defouling, erosion, and basically turning into microplastics. And there is strong evidence for this. In this particular report, the Santa Barbara Basin coastal sediment was studied. Researchers found that the deeper or bottom layers of sediment dating to the 1800s contained really no microplastics, while the upper layers of sediment dating to the 2000s contained a lot of these plastic fibers and fragments that you see pictured here. They found that plastic deposition rates were directly correlated to plastic production, and coincidentally, human population increase as well. So I think this is relevant for me to bring up this point because it's here in these coastal land, these coastal waters, where the onset of microplastic production begins before its rampant proliferation into everything in our lives. And with the onslaught of new plastic that will inevitably undergo this transition, I think it's important to study microplastics in coastal waters, coastal sediments, along with microplastics and other things. It's important to study microplastics in all matrices. So Frontier Laboratories did publish an application note on microplastics identification in this particular article on coastal surface water collected at Osaka Bay. This article also demonstrates the use of the microplastics F-Search library, which we will get to see today, and you can read this article for yourself, along with other articles written by our very own Rogine and William Pipkin, our guest, at our website at lqa.com. So allow me to take a little time to explain who we are at Quantum Analytics, LQA. We are a value-added distributor of multi-vendor analytical instruments. What this means is that we don't just provide a solution in the way of instrumentation. We add value through technical services, application support, financing option. We have renting options, leasing options. We have refurbished instruments that you can see on our website at lqa.com, as well as an online store. And because we don't just have reach in the chromatography field, we do have reach in microscopy, spectroscopy, as well as systems like the Frontier unit that augment your chromatography experience. We are able to integrate across platforms. Quantum Analytics has 30 years in the business, and we have many channel partners that we work with, including names you already know of like Agilent Technologies and Frontier Laboratories, who we are partnering with for our webinar today. A little history on Frontier Laboratories. They were founded in 1991 by Dr. Chu Watanabe. Toussaint, along with his fellow chemists, developed the vertical microfurnace technology. Frontier Laboratories also hosts a number of accessory units that augment the pyrolysis system. They have a line of ultra-alloy stainless steel capillary columns, and of course they have the F-Surge and microplastics F-Surge library. Frontier Laboratories is headquartered in Japan, though they do have an office here in Houston, Texas, just like us, and they do have global reach as well. So what exactly is this vertical microfurnace technology I keep going on about, and why is this related to this topic of microplastics? This furnace sits right on top of your GC. You can see it pictured here. It interfaces directly with the inlet. In fact, there's a needle in there that punctures right through that inlet septa, and this involves no transfer line. So everything that you're pyrolyzing in the furnace goes right through your inlet to be separated and analyzed. In traditional GC, we're really limited to volatile or semi-volatile compounds that are conducive to the GC inlet temperatures. However, with a furnace, we're able to characterize larger molecular weight compounds, including polymeric compounds, such as in microplastics. So here's a little cross-section of your microfurnace. This furnace houses a quartz tube. This is where the sample cup is dropped into to be pyrolyzed by the furnace. The sample cup pictured here only requires microgram amounts of your sample, as is cut, scraped, punctured, or whatever have you from your polymer. And once pyrolysis begins, all of the pyrolysates or the products of your thermal sampling are swept right into the inlet to be separated and analyzed by the column detector. The sample cup is only dropped into the furnace when the furnace is heated and ready. So this means there's no degradation, evaporation, or thermosetting before analysis occurs. This is a true pyrolysis reaction, and this furnace reproducibility is plus or minus 0.1 degrees Celsius, and it is precision measured. So that means when you're controlling that furnace temperature remotely, you're actually pretty close to controlling the sample temperature as well. Unfortunately, this furnace is not a one-trick pony. It does have multiple modes of operation, and these different modes of operation are probably best explained by the method map that you see pictured here. Often with this system, we begin with an evolved gas analysis, or EGA, and then from there we can determine thermal desorption, pyrolysis, or double shot techniques. And this will make a lot more sense as we go through the next slides. As I've mentioned, often we begin with an evolved gas analysis. In EGA, we have your pyrolyzer, which is on top of your GC, with a deactivated metal tube kept at an isothermal temperature that feeds straight into your detector, NMS in this case. When the sample cup is dropped into the furnace, the temperature is ramped, and while that's happening, all of your pyrolysates are going through that tube and collecting at the MS. So what you get at the end here is this nice thermal profile of your sample, which we like to call the thermogram. And don't forget, at each point in the curve, you can collect the mass spectrum. This EGA thermal profile will really facilitate how we navigate the other modes of operation. Example, in thermal desorption, we switch to an analytical column this time. The sample cup is dropped, the temperature is ramped, just like in EGA, but we have now separation of all of the pyrolysates that you thermally sampled, and you get a nice chromatogram at the end. This is really ideal for things like additives or any lower molecular weight compounds that you may want to thermally desorb out of your sample. In flash pyrolysis, the sample cup is dropped into a heated furnace and it's sampled isothermally. The result is a pyrogram of the various components in your polymer that was pyrolyzed at whatever temperature that you programmed it to. In this particular example, you have your additives and your polymer that's coming out at that particular pyrolysis temperature. Double shot combines both of these techniques. The sample cup is dropped into the furnace. It's thermally sampled to extract out any additives. The cup is dropped back into a heated furnace this time to be flash pyrolyzed. You get at the end 2 pyrograms or chromatograms of your pyrolysates. So the pyrogram of your polymer is truer to the polymer backbone of your sample because you thermally desorbed out all of those additives and your lower molecular weight compounds. And you can get really creative by adding multiple steps of thermal desorption in something called heart cutting, and the cup will be dropped up and down the furnace so it's protected from heat when the various chromatograms are being collected. Okay, so I think that you guys should be now experts on pyrolysis. You don't need me anymore. Except, or maybe you think that there's a lot here. There's a lot of data pools, thermograms, chromatograms, pyrograms, mass spectra, and maybe it seems a little complex, and it is. This system is complex, but only to the extent that it can add nuance to your microplastics research. This large data pool of pyrograms and thermograms and chromatograms and what have you are easily digested by the F-search engine, which can be used to search the additive libraries, the polymer libraries, the pyrolysis library, the EGA library, and it is simplified and easy to navigate for this particular purpose. And the newest iteration of F-search is the Microplastics F-search library, which really facilitates this emerging research into microplastics. But I think that I've teased you enough with that. I'm going to go ahead and hand it off to Regine. So Regine, please take it over from me.
Fantastic. Regine, I'm going to make you the presenter so you can share your screen.
Perfect. So now my screen should be shared.
Yes.
Perfect. All right. Well, thank you, Lauren and Khadija, for the nice background. So let me put this. All right. So today, I will talk about the microfurnace Pyrolysis-GC system configuration that we offer specifically for microplastic analysis, the workflow of the analysis, and what is F-search MP 2.0. And then at the end, I also will show the F-search software and how it can perform quantitative analysis on microplastics. So Pyrolysis-GC enables a direct analysis of solid and liquid samples and can be applied to different types of samples that are even insoluble due to the large molecules and cross-linked structure. As you could see from this slide, we've developed a Pyrolysis-GC system that is optimized for the analysis of microplastic in environmental samples. With this special data analysis software, which is called the F-search MP 2.0, even if you don't have experience in polymer analysis, you could easily use this technique. The analysis procedure, including the identification or the quantification, is automated using the AutoShot sampler, and the results can be obtained in less than 1 hour for each sample. So as you could see here, the system consists of a GCMS system. And the heart of the system is the multi-shot pyrolyzer that is called EGA Pi 3030D, which is our patented vertical microfurnace pyrolyzer based on a ceramic furnace. The sample is heated into the furnace to form gaseous pyrolysates, and then they're all introduced into your GC column directly and continuously. So as you learned, this is a single-step flash pyrolysis that is, everything is directly and continuously are getting transferred on your GC column. There is no transfer line. You can also see the AutoShot sampler that is on top of the pyrolyzer, and this accessory can automate a continuous series of analysis up to 48 samples. F-search MP 2.0, which is our patented and unique search library that allows you to obtain reliable microplastic identification and quantification analysis. And then, as you learned, we also make the ultra-alloy capillary columns that has superior inner and resistant against bending, heating and contamination due to the gradient multi-layer deactivation process. And also you can see the vent-free GCMS adapter that allows you to quickly switch between the separation column and the EGA tube without venting DMS. And lastly, the microplastic calibration standard set that you can use for creating calibration curve and quantification work. So here, I'm now showing the workflow of microplastic analysis using your microfurnace. Step 1 is your sampling and pretreatment, depending on the type of the sample that you have. Step 2 is to place the sample inside your sampling cup and then place it into your auto-shot sampler and perform the pyrolysis, that easy. And then step 3 is the data interpretation using your AppSearch. So in terms of sample preparation, microplastics are typically extracted from environmental samples by performing appropriate pretreatment and then homogenized using a grinder or a mixer. Then you can place your unknown sample or the standard sample into your sample cup and weight it using your microbalance in most cases. However, as part of our calibration kit, you get the diluents of SiO2 and CaCO3, which you can see here, that they allow you to eliminate the need to have a microbalance. So you can use a semi-microbalance and prepare your own calibration standards to measure small amount of samples as well. So the SiO2 and CaCO3 diluent have a similar functionality to solvents in terms of sample preparation. In a simpler words, if I want to really describe the functionality of them, I could say that they are your solid solvents that you can really use for creating your calibration curve. So here is the overall sample preparation flow. You place your environmental sample or the microplastic calibration standard into your sampling cup. You weight your sample, and then if you're using the auto-shot sampler, we suggest that you cover the sample with quartz wool to protect your sample, and then start your analysis using the microfurnace. So now let's talk a little bit about the calibration standard set. So the microplastic calibration standard is used to identify and quantify microplastics using your microfurnace Pi GCMS. Basically, it allows you to easily create any calibration curve for quantification of your microplastics. Two microplastic calibration standards with different diluent, SiO2 or CaCO3, are available as part of the set for you. Both samples contain a few microgram each of commonly used 12 polymers, which are homogeneously dispersed with a solid diluent for easy weighting on a semi-microbalance. In addition, as I mentioned, as part of the calibration set, you also have the diluent SiO2 and CaCO3 that you can use for preparing your own standard samples. And this table here shows pretty much the content for your microplastic calibration standard set. So now that you have that set with 2 or 3 different type of calibration standards, how would you choose which calibration standard you would like to use or use it as the first step? This table here can guide you to select the appropriate microplastic calibration standard. So you can select the type of microplastic calibration standard based on your target polymers, the microplastic polymers. Now, if you don't have any targets at first, we suggest that you start with MP's CaCO3 standard that can target pretty much all the 12 polymers, but with low sensitivity to PET. So in that case, if you're going after PET and or PC polycarbonate, you can use MP's SiO2 with TMAH. TMAH is an alkali reagent. It's tetramethylammonium hydroxide. This is a reactive pyrolysis where you add this reagent into your sampling cup with your sample and then perform pyrolysis. And the suggested temperature is at 400 C. The other two, the MP's SiO2 and MP's CaCO3, they are just flash pyrolysis simply at 600 C. So also as shown in this table here, with MP's SiO2, PU cannot be targeted because its quantitation peaks react with PET and nylon 6,6 pyrolysate. So in this case, if you want to do PU, you would want to start with your MP's CaCO3 standard. So really this table serves as a guide to use your probable calibration standards based on your target for that 12 common MP's polymer. Also, I like to mention that FSMP 2.0 allows you to create your own in-house libraries as well. So now moving on to the other parts of the system configuration, the UAMP column kit, which is ultra-alloy. UA stands for ultra-alloy microplastic column kit that consists of a separation column. It's a UA5, that's a 5% diphenol, 95% PDMS. A pre-column that we call it UA pre-column 50. It has a medium polarity, and also a UA connector. So this kit, everything including the column and the pre-column, really improves the accuracy of qualitative and quantitative analysis of plastic mixture sample using F-Search MP 2.0. Also, this product reduces the contamination of the separation column, thus reducing the replacement frequency of your column. So here I'm showing one example on the right-hand side on how the UA pre-column actually improves separation and identification of a C8 pyrolysate, which is generated from PE from cyclophenodiene that is a pyrolysate of nylon 6,6. So with the UA pre-column, these co-eluting pyrolysates of PE and nylon 6,6 can be separated and identified. Now moving on with another part of the complete solution for microplastic is the packed GC glass insert. So we also developed a packed GC glass insert that's pretty much your liner or your GC to improve the peak shape of the pyrolysates generated from microplastics. So in addition to also a better peak shape, the packed GC glass insert can improve the accuracy of your qualitative and quantitative analysis of a specific plastic in polymer mixture sample using F-Search MP 2.0 software. And you can see an example here how the abnormal peak shape and the lower peak height are improved when you are using that packing of the GC glass insert. So step 4, which is the last step as I just mentioned, it's the interpretation of your quantitative result of your F-Search or actually qualitative result of your F-Search. So after running your samples and your standards, you would use your F-Search MP 2.0, specifically for microplastic analysis in this case, to perform both quantitative and qualitative analysis of polymeric components of your sample. So for example, if a quantitative result from F-Search MP shows that the sample contains 40 microgram of SBR, this result only represents the polymeric component in a sample. So it's important for you to also consider the weight of inorganics and the additives to make your conclusion. So basically, as you know, with Pyrolysis-GC, you're analyzing the organic fraction of your sample. The inorganics remain inside the cup, and the additives can also be identified using F-Search 3.6 libraries. That is a broader MS library engine we offer for evolved gas analysis, thermograms, additives, and polymer analysis as well. But this F-Search that I'm focusing on today, that is F-Search MP 2.0, that is specifically for the microplastic analysis. So before I go to more detail in F-Search microplastic, this is an app note, short technical note about identification of colored microplastic sample, the marine color plastic microplastic sample. And this analysis is the qualitative analysis and was used from the F-Search 3.6. So we had 6 different colored MP samples that we collected from the surface water at the Osaka Bay. the samples were cut into very small pieces, and then we placed them into the sample cup. Pretty much that was the all sample preparation that were needed to make them smaller pieces to put them inside our sampling cup. Then we perform flash pyrolysis at 600 C, and again with micro furnace, you are performing true and single step flash pyrolysis. And this analysis is for qualitative analysis in this specific techniques that I'm showing here. So using the F-Search libraries 3.6 version, sample A was identified as polyethylene. And how we identify it was we're just seeing the fragmentation of our polyethylene when it breaks down in a random scission manner, and how F-Search was identifying every pyrolysate to its corresponding polymer. And that's how F-Search allowed us to identify those specific pyrolysates to polyethylene as part of sample A. And then sample C to F showed almost the same pyrogram as you could see here, and they were identified as polypropylene. So they were pretty simple samples because it was just one polymer. But then when it comes to sample B, from our FTIR measurement, sample B was identified as ethylene propylene type polymer. However, sample B also shows peak ascribed to isoprene, styrene, and butadiene in its pyrogram from the Pyrolysis-GC. So more detailed info, which suggested that sample B is composed of both a natural rubber and a styrene butadiene copolymer. So before I go ahead and do a live demo of the F-Search MP's operational procedure, I thought it's better to show you guys a little bit of slides about each step, so that way you have a visual understanding of how the F-Search does the step, and then we'll go ahead and jump into our live, showing you guys a live way of how F-Search does the quantitative work. So this is F-Search MP's operational procedure. Step 1 is actually to create a plot of the retention index and retention time, where the retention index is based on polystyrene fragmentation. And then step 2 is to create the calibration file that is based on the pyrograms of your microplastic calibration standards. Step 3 is the search results of microplastics. And then step 4, which I find it very important, is the confirmation of the searching analysis that you just got obtained from the F-Search. So this is step 1, and again, I'll show that in a few seconds via the live demo, but this is to just give you guys an idea of how the software will do that for you. So step 1, you pretty much load your sample, and then you do the RI calculation, and that's based on the pyrolysate of polystyrene, and you'll see that the system automatically will do an auto detection of the RI, but at the same time, you could see that they are you could also change the values, especially when it comes to the retention time, in case you want to have a little bit of a different retention index, but the system will automatically will do the RI. The second step will be creating calibration curves. In this case, your calibration curve will be based on the quantitative EIC, which is the extracted ion chromatogram peak for each of these polymers. So the way really the FSMP 2.0 functions is there is a characteristic peak, we call it EIC, extracted ion chromatogram peak for each of the polymers. And that's how F-Search will identify and quantify based on those EICs to be able to quantify those polymers. This is a step 3 where the software will provide you with the results of qualitative and quantitative work. You of course have the plastic name or your polymers that are here. And then you also get a library match quality in percentage. So how well of a quality match each polymer is. And then you also will have the microgram amount and the percentage, the weight amount, and the peak area. So this table really gives you a lot of detailed information that you could see, not even the weight percentage, the microgram probability, but also a nice bar graph of the percentage amount of your polymers for the microplastic samples, the mixture. So step 4, that's actually important step, which is a confirmation of the surging result, where you'll be able to, using the software to, for example, I'm showing a PE here, PE polymer. So you can see the marker peak of the sample, of your sample on non-sample, and you can compare it to the marker peak of your microplastic calibration standard for the calibration. And same here, you could see the spectrum of your sample versus the spectrum of your standard inside the polymer. And as I just mentioned, each of those polymers has its own marker peaks and ions. So you want to check peak shape, you want to check the retention time, mass spectrum, and integrated peak area. That way you can be confident that the results are pretty matching with the F-surge, and this is the true values or percentage of the polymers inside your sample. So now I'm gonna go ahead and show you guys the live demo of the F-surge MP 2.0. Okay, so all I did before the webinar starts, I just opened my F-surge window, and that's pretty much what it comes when you open your F-surge window. What you want to do first is to load a sample. So for the purposes of today, for the demo purposes, I am doing a 2-point calibration with running with n equal 2, so 2 sets of each of my calibration point. Typically, you want to do 3 to 5 calibration point, but for the purposes of demo, I'm just going to show this 4 total run. That was a 2-point calibration curve, and I was just using SiO2 standards. Again, depending on your target, you could have done CaCO3, so it doesn't matter really. I'm just showing the SiO2 here. So I'm just going to load my standard sample, which was MP's SiO2. This was the first set. And you'll see nicely done, this is the retention time, these are the intensity, that's the TIC, total ion chromatogram on the top. When you go to your library, when you want to select your libraries for search, this is where you would pick the appropriate calibration standard that you picked. In my case, I'm using SiO2, but if you want to use the TMMH, the reactive pyrolysis, or CaCO3, you would just simply check those boxes. But for my purpose, it's just SiO2. Now, if you have additional polymers, then more than those 12 polymers, then you could create your own user library. And if you would do that, they will actually show up here, and I could check the box simply for my own user library as well. So first step first, as we discussed, we'll go ahead and do retention index calculation from the standard sample. And here on the bottom, you can kind of see that it was doing this for you, okay? So these are the retention index calculation from Poly standard that is auto-generated. Now, if you want, for any reason, your peaks, you want to go in more to detail and maybe change instead of 4.980 to 4.90 or 4.982, you could do that, and it will, of course, automatically do it for you. In this case, I'm just going to use the default auto-generated retention index from F-surge. Then the next step will be to create your calibration curve. So when you get these microplastic calibration standard set, as I talked about it during my slides, you get the diluent of SiO2, CaCO3, as well as MP's SiO2 and MP's CaCO3, which are those 12 common polymers that are immersed into the SiO2 or CaCO3 to make the calibration standard for you. So in 4 milligram of your MP's SiO2, there are some theoretical values of each of these polymers that are given to you. So you know these values, we provide that to you guys as already a made calibration standard sample for you. So here, my first point of calibration was 4 milligram. Now, if you decide to do lower or higher, you could totally do that. You just have to calculate the amount of your polymers in how much of a calibration standard you want to put inside your cup. Mine was 4 milligram, the first one, and I know in 4 milligram, the amount of PE is 160. So, okay, good point. Before go ahead and being able to enter the amount here, first I need to enter, I forgot this is a step, you need to enter your calibration level. In this case, I'm doing 2-point calibration, so I say 2, apply. Are you sure you want to set it as 2? You would say yes. And now it allows me to go ahead and change the amount based on my first calibration standard, which was 4 milligram, and the amount of P is 160. PP is 40. PS is 8. ABS 16. And again, these are given values to you. SPR is 16. These are already pre-made for you, but you're just entering them here because you want the software to calculate the next calibration curve point for you based on your first entered information. PMMA is 8. PC is 4. PVC is 40 micrograms. PET is 16. Nylon 6 is 5. Nylon 66 is 18. If you would have used CaCO3, you would also see the PU in this polymer list, but here, as I mentioned, PU pyrolysate, the characteristic ion will react with nylon 66 and PET. So if you targeting PU, you want to use your CaCO3 standard. In this case, I'm not. So these are the theoretical value that I just entered for 4 milligram. And now what I would do, I need to add the representative files, which are these 2 files that I ran, twice of the 4 milligram of sample. And then the setting is not complete, so it will go to the next level, which is index level 2. So my second calibration curve, I did 1/10 of my first one. So the multiplier will be 0.1, and look at all these numbers that I originally entered for my 4 microgram. Then I did multiplier 0.1 because I did 1/10 of it. So when I apply, the system automatically calculates that for you. So all I need to do, go ahead and add the other standard that I ran, twice of them, 1 of 10. So everything looks good. You could say next. So now it is detecting and creating the calibration curve for you. Again, at the bottom, you can see the process. So for the user who are on the call right now and they're using FS 3.6, very similar software, but you have also the EGA, Evolved Gas Analysis Thermogram libraries, additive MS libraries, Pyrolysis MS libraries, and the polymer. But this is the MP 2.0 that is specifically for the microplastic analysis. So very quickly, you'll actually see the qualification file. So this is where you can actually check and make sure everything looks good based on your standards that you ran. So you see the polymer name here. These are the characteristic peak or the EICs, as I mentioned, the M/Zs that we extract for each polymer to be able to use the app search, retention time, area, and simply you can check each polymer and you can actually manually change that integration here. So you can click on PP and this is your first set. You can also go to your next sample and you can check and make sure everything looks good. Again, if you don't like an integration, you could easily change that manually for yourself. So once you create that qualification file, you want to save it. In this case, I'm not going to save it because I already done. This is a demo purposes, so you'll just save it. I'm just going to cancel it. And the last step will be simply to go and using your file, you just want to load that quantification calibration data that you just saved. So you load that. Mine is this one. Last step simply will be searching for the microplastics. So really in 4 simple steps, you're analyzing your microplastic. And again, I'm using just a 2-point calibration curve. In most cases, I think 3 or even maybe 5-point calibration curve will be more practical in a real world. Nice. So this is pretty much the slide that I was showing you guys, how the F-search will bring the results of your microplastics. So it's so much going on here. Let's go ahead from the top so you can kind of see the search results could be based on a spectrum or extracted ion chromatogram, and I'll show that in a few seconds. Here, your display threshold, this is something you could set. I set it as 80%. These are the polymer names, those 11 polymers. These are the probability, the amount, the percentage of them. These are the microgram, the ratios, the area, the retention time, and all these, also the bar graph at the end. So the confirmation step, which is the last step, will come in place when for each polymer, for example, as soon as I click on each polymer, you can see the corresponding window on the right-hand side, and these are the spectrum. So for the polyethylene, the top one is your unknown PE spectrum, the bottom one is the library. So you want to make sure they're matching pretty well. And in this case, the matching is pretty high, but it's always good to kind of confirm and make sure your spectrum for the polymers, they look pretty much the same. So ABS, PVC, you could check that all individually. And you can also click on EIC, extracted ion chromatogram, where for each polymer, for example, for PE, that's the unknown PEIC, extracted ion chromatogram of 82 versus your polymer, the actual calibration standard from the library. So this is PP and then PVC. So that will be the confirmation part that you want to check and make sure the spectrum and your EICs of your unknown samples are matching very well with your library.